Today I'm going to be showing you how to complete the 3D modeling operation for the ACME thread for the table lamp, and this will introduce us to using the COIL feature in Inventor. So taking a look at the machine shop drawing sketches here, that is being shown right here. So this is the ACME thread. So it is shown as 1 1/4 inch diameter, and it says 5. Now, this stands for 5 threads per inch. So basically what that means is for every inch long you measure on a shaft, you should be able to count 5 threads in that inch, right? That's how threads are usually designated, as well as their types. So ACME thread is considered to be the second most powerful thread in existence. The strongest thread you would find would be a square thread, but the ACME thread typically replaced it because of the difficulty it was or is to cut on a lathe. And cutting a thread on a metal lathe is actually a bit of a complicated operation. It involves a lot of setup and a little bit of skill, being able to engage a number using a split nut lever. So basically, machine shop terminology and how to create the thread we're not really going to get into, because we're not really worried about that, because we're looking at this from a drafting and design point of view. But ACME thread is typically defined as a power thread, and it's typically found on your bench vices, for example. Something that you see in a shop classroom, which allows the movable jaw to thread in and out towards the fixed jaw on a vise. You may even have something like this at home in a workshop if you have a workbench and a vise attached to that workbench in your workshop or garage, for example. So just a little bit of backstory on the ACME thread. Let's go back. And we're going to come up here and we're going to look at this link here. This is from Wikipedia. This is the trapezoidal thread form, which is what an ACME thread is. So this is a very good explanation of ACME thread characteristics. I'd encourage you to read through it, but I'm only going to be going through the most important parts of this. And this is what we're basically going to be creating in Inventor, is a profile that looks like this. Now, we need to understand some numbers before we do this. So the basic ACME thread profile is shown here. So the angle used in the ACME thread is 29 degrees. So we must adhere to this. P stands for pitch. And this center line, right, exists in the center of the thread from top to bottom, from the outside diameter to the full depth. One space through one thread is your pitch. And then obviously your pitch is divided by 2 going from the top diameter to the bottom, because this is divided over 2 sides, because this is a cylindrical object. So whenever you're dealing with a cylindrical object, you're typically taking something and dividing it by 2, because it's shown fully over 2 sides. And we're only looking at one top profile of a cylindrical object right now. Going back, we need to know what the pitch is. So we need to come down and look at this chart here. Nominal diameter. If I find this here, I see 1 inch and 1 1/4 inches. Well, this makes sense to us because our outside diameter is 1 1/4. So our pitch is shown as 1/5. Also, the equivalent would be 0.200. And what does that give us for our thread density? In other words, that's also known as TPI, which stands for threads per inch. 5. Right? So we're going to be drawing this to an exact industry standard according to the machinery handbook. So we're using all the proper numbers in our sketching, in our modeling to complete this. So that's basically all we really need to know. So we're going to continue on, and we're going to switch into Inventor now. Now, I've already gone ahead since the previous lesson and I've included the Q drill. Now, I haven't done this in front of you, and I'm not going to do this in front of you. That's your job to go online, find out the diameter of the Q drill, and place it in here. And I've already done it here with a hole number 1. That's it right here. So you can either do this with a point and hole feature, or you can do this with a circle and extrusion cut feature. I don't really care which one you use. Both are fine. Now let's continue on and let's take a look at how to do this thread. So I'm going to be orienting this to the front. I'm going to be going into this direction. I'm going to be doing this modeling procedure much like I would be doing it on a metal lathe. So I'm basically starting with a solid 1 1/4 inch diameter of solid aluminum. That's this diameter right here. And we're going to activate the coil much like we would cut it on a lathe. So we're going to cut into it and we're going to extrude, cut material away to add the thread, much like a machinist would do it on a metal lathe. So to get started, we need to create a work plane first and put the work plane dead center in the middle of the spindle through the length. So we're going to go origin. We can use the YZ plane. This is fine. Activate it, highlight it. We're going to hit plane. We're going to pull the plane out, and then you can just set this to 0, right? Because we want this to be dead center. It has to be center because a tool bit would have to be set at center height to be able to cut that thread. So it's the same type of theory in CAD as it would be in an actual machine shop doing this on a metal lathe. So what we have to do now is actually draw that thread profile. So we're going to do a 2D sketch, and we're going to select the work plane, and we're going to draw that trapezoid and attach it right here to this corner. So we're going to hit line. We're going to snap. Wait till that green little circle endpoint snap shows up, and we're going to click. And we're going to sketch a basic trapezoid shape. It has to be drawn like this, the same way a high-speed steel tool bit or carbide insert would be plunged into the workpiece to do the cutting on the lathe. Right? You're going to be starting with the smaller cutting surface first and working your way up to a larger one, like this. This is a trapezoid. So it's attached. So this line is purple as it should be, and we have to constrain the rest of the sketch. So we know that the angle must be 29 degrees, so we'll start with this. Before I set the angle, because I just, roughly sketched this shape, I don't know that this is equal on both sides. So what I'm going to do is go up here, get the equal constraint, and select this line and this line, and it's going to make them equal. So that's very, very important. After we've made them equal, we can run a general dimension from here to here, and we can set that angle to be 29 degrees. Okay, next up, we need to draw a line in the middle of this profile from this side to this side. So I'm going to use a construction line for this. I'm going to select construction line, push it in, get the line, find the midpoint of this trapezoid, and draw a line horizontally from one side to the other. And that will create that middle line that I'm going to be using to create a dimension. So switching back to here, we have to set the pitch. This pitch is going to be divided by 2, right? Because I'm only drawing one trapezoid here, right? I don't need the full pitch, right? I'm only going from here to here. So from here to here and here to here is the same distance, right? This is the same in the open space as it is where the actual thread tooth form exists. So I'm taking my pitch and I'm dividing it by 2. And I'm just going to be running a dimension from here to here, and I'm going to be taking my pitch and dividing it by 2 like this dimension dictates I should, right? So this should make sense because I've only drawn one trapezoid. I haven't drawn 2 of them, right? I got to divide this by 2. So general dimension from here to here. So our pitch is 1/5 divided by 2. That's going to give me 100, right? Because we know that the pitch is the full pitch is 0.2. And lastly, one dimension from here to here will fully constrain the sketch. And again, it's the same thing. I'll just type 0.1 because we know it's the same number. All right, so this has been constrained. Now if I go to finish sketch and I go to COIL this, right here, got away from me there. All right, creates a helical coil spring or thread feature. Now it won't work because I need to have an axis to be able to rotate the profile on. So I need to create a center line that's going to be passing through the entire length of the spindle. Right? So if I hit COIL, I can select the profile, but nothing will preview, nothing will happen. So I'm going to cancel that. And I'm going to temporarily remove half the spindle. I don't need to actually do an actual extrusion for this. This is going to be a temporary thing that as soon as I'm done drawing my center line, it basically should restore itself. So I'm going to select the plane here. And well, before I do that, I need to actually start a new sketch. So start 2D sketch, select the work plane. Let's go back into an isometric view for a minute. And right click, and then go up here and pick what's called slice graphics. And what it does is it slices half that spindle away. And I can actually kind of see more clearly inside now. This is helpful. So now I can switch to my left view. And I'm going to pick a line. And I'm going to select center line. And I'm going to start here in the middle. And I'm going to draw from that side to the end. And click this endpoint. And that's going to create the center line, and it's already constrained. It's already purple because it's on that Z axis right now from one side to the other. So once I've done that, I can hit finish sketch, and I'm ready to actually coil this thread. So I'm going to select coil. We're going to select the profile, so push in profile, it's going to highlight. Then we're going to select the axes, and we're going to select that center line. So we have to actually pick that mouse cursor. We're going to select the center line, and what it does is it begins to preview the start of a coil. So we're getting somewhere now, but again, this isn't going to work out the way it should. We have to make some adjustments to it. So we're going to click over to coil size, and we're going to have to set the pitch. And we've talked about the pitch. The pitch is 1/5 fraction. And we also need to change the type from pitch and revolution to pitch and height. Now, so it counts height as length, right? Even though we view this as length, Inventor will think of this as height. So this is not going to reach. So we're going to have to extend it. So what is the length of that diameter? Well, it's 1 1/4. Right? Diameter is 1 1/4, length is 1 1/4. All right, so I'll change this to 1 1/4. Let's look at it now. It's actually not going to reach, right? In theory, the tool bit on the lathe is cutting air, and then it starts to dig into the workpiece. Of course, it doesn't get cut at the finished depth as we're doing it in CAD. Of course, we can get away with things like that in CAD because, you know, we're doing things in a virtual world here. But it's going to stop somewhere here, and it's not going to give you the full length or height. So we're going to just give it a little bit more. So look at this coil preview as I change this to, let's say, 1.5 inches. And now look what it's going to do. It's going to start here, it's going to go through, it's going to clear. So it's going to continue on through the 1 1/4 length. It's going to come out, and it's going to be cutting air until it finishes at 1.5 inches. All right, we're just about ready here. The last thing we need to do is go back to coil shape and pick cut, because obviously we're cutting material away in this operation. So once we've done that, we're going to hit OK, and there we have it. There is our perfectly modeled ACME thread on 29 degrees at the proper helix, a pitch of 0.2, 5 threads per inch. Just as it would be done on a metal lathe in real life, right? And this is exactly what I did so many years ago in high school. I did this project, and I actually cut this on the lathe. And you can see that thread right there. It looks exactly like this, right? We're also going to be creating another thread here later. But that's going to be the lesson for today. And we're going to, again, take this work plane, and we're going to turn off its visibility and hit save. And that's it for today. So a very neat lesson on how to do a more advanced modeling procedure in Inventor. Now, I've actually already 3D printed this, as you've seen, and I could actually 3D print a nut with the internal ACME thread, and I would actually be able to screw the nut onto the 3D printed spindle. That's how accurate the modeling in Inventor is to actual machine shop practical work and the 3D printing. Right? 3D printing is something we're going to be looking at after this project. We're going to be doing a prototyping and product design. So that's something that'll be coming up later. So I'm going to sign off for now. I'm going to let you try this today. Take care and have a great day.